All right, let's solve a trigonometric equation. This one's a little bit more difficult that we have sine squared of theta equals 2 cosine of theta plus 2. We want all the solutions for theta between 0 and 2 pi. First thing I notice on this is we have both sine and cosine. So basically, you can kind of visualize these as two different variables going on here. We would rather solve an equation that only has one variable. So as you can see, the hint on this one is rewrite it all in terms of cosine, which is what I would do from the beginning because there's no obvious like common factor to factor out or something along those lines. So what I'm going to do is I'm going to replace sine squared of theta. I'm going to replace it using the Pythagorean identity. So the Pythagorean identity, as you may remember, is cosine squared of theta plus sine squared of theta equals 1. And this shows up quite often whenever you use squares along the way, that I want to replace sine squared in terms of cosine. So I'm going to rearrange the Pythagorean identity. And move the cosine squared to the other side. So I'm going to subtract it from both sides. So we get sine squared of theta equals 1 minus cosine squared of theta. I'm going to replace that in on the left-hand side. So now we have 1 minus cosine squared of theta equals 2 cosine of theta plus 2. Now we have an equation that only has cosines involved. So what I'm going to suggest is we get everything on one side and try to factor it. Now, a lot of students get intimidated when they see problems like this where we have cosines more than one place. It does feel intimidating when you first get going on these. One strategy I always suggest is just rewrite this so it's back to a basic variable that you're comfortable with. So what I'm going to do is do kind of a side equation and replace wherever I say a cosine of theta, I'm just going to replace it with an x. So we can say this is 1 minus x squared equals 2 times x plus 2. If we can solve this equation down, it's going to be very, very similar steps to solve the equation we really want to solve down. So what I'm going to do is just over here on the side equation, let's move everything to one side and get 0 on the other side. So I'm going to move everything to the right-hand side. So I'm going to subtract 1, and I'm going to add x squared. So that'll put 0 on the left-hand side here, and we'll get x squared plus 2x plus 1. And then we want to factor the right-hand side. Zero product property, using our factoring. Hopefully this is one we're comfortable factoring without, say, pulling out the AC method or something else. We'll split up the x squared evenly as x and x. We'll split up the 1 evenly as 1 and 1. And we'll make these both positive so that our outer and inner terms make a positive 2x. Like I said, pretty similar work that we're going to do over here on the left-hand side. Let's move the 1 to the other side. So I'll subtract 1. Let's move the cosine squared to the other side. So I'm going to add cosine squared of theta. So that'll put a 0 on the left-hand side is equal to cosine squared of theta plus 2 cosine of theta plus 2 minus 1 makes 1. And then it is going to be very similar as far as our factoring would go. Two binomials, we don't have a common factor across the board besides 1. We'll split up the cosine squared. So cosine of theta and cosine of theta. We'll split up the 1 as 1 and 1, and we'll make sure our outer and our inner can combine together to give us a positive 2 cosine of theta. So we'll make them both positive. As you can see, pretty similar work, thought process. If you have a different technique for doing your factoring, you certainly can use the AC method or all these other methods I've heard about over the years. But get it factored, do a side problem if that's handier. If you can wrap your head around it a little bit easier with x's involved instead of cosine of thetas. But we still need to solve this. So since we have two of the exact same factors, we can set simply one of these equal to 0. You don't know which one because they're the exact same. And then let's work on isolating the cosine of theta. So I'm going to move the 1 to the other side by subtracting it. So that'll give us cosine of theta equals a -1. Now, whenever we're dealing with ones or negative ones or zeros, where I like to go back to is think about points on the unit circle. So our unit circle, if I quickly draw one in here, hopefully at this point we're comfortable with our cosine is always going to be the x value, while the sine is always going to be the y value for points on our unit circle. All right, we're trying to figure out when is cosine of theta going to equal a -1. So that's telling us that our x value for any of these terminal points has to be -1. Well, that only happens over here on the left-hand side at this point. That would be the ordered pair -1, 0. And that corresponds with an angle wrapping halfway around. This quadrantal angle is going to be at pi. So our solution is going to be theta is going to equal pi. And because ours was limited, our theta had to be between 0 and 2 pi. That's the only time around the circle that's going to happen, is going to be at pi. Now, I will go ahead and say that if you were not limited between 0 and 2 pi, instead, if you were asked to give all solutions, how you would represent that, it would be our pi, the same value we just found for our angle. But on the end, you would add 2 pi, right? That's the period for cosine, multiplied by k, where k represents some integer. Basically, what you're doing here is you're finding coterminal angles. If you added 2k times 1, 2 pi times 1, that's going to be adding 2 pi, which would mean you go around the circle one more time in the positive direction, and your terminal side ends up in the exact same place as pi. Its terminal side would land over here as well. All right, so this formatting would be if it's not limited. However, ours is limited between 0 and 2 pi. So our only solution on this is going to be pi. Hope this helps out. Write it in terms of just one sines or cosines, if at all, from the beginning, and then factoring. Write a side equation like this if it helps out in wrapping your head around your factoring. All right, good luck.